The second consequence of Einstein's postulates is what we generally call time dilation. So here, two events occurring at the same location in one frame will be separated by a longer time interval in a frame that is moving relative to the first. Okay, so now let's imagine that we have the Starship Enterprise here that's moving with velocity v relative to the Earth. Okay, the Starship Enterprise, we're going to assign the primed coordinate system to that, S prime, and that coordinate system, the S prime coordinate system, is in the rest frame of the Enterprise. Earth, we're going to assign the coordinate system S, which is the rest frame of the Earth. Okay? Now, let's imagine that we have a clock that's ticking in the frame of the Starship Enterprise. So let's imagine that we have a clock in here, okay, that's going tick, tick, tick. All right. Now, the time dilation says that the ticks of the clock that are in the Enterprise, as observed by an observer on Earth, will take more time will pass between ticks for the person who's on Earth than the person who's actually sitting in the Enterprise. And so, in other words, delta t is greater than delta t prime, where delta t is any time interval as measured by a clock on Earth, and delta t prime is the time interval measured by the clock in the Starship Enterprise. So to summarize, each tick of the clock is an event, okay, and all observers, no matter what frame they're in, must agree that the events occur, okay, that all the ticks on the clock actually occur. But time dilation, this consequence, time dilation, says that the time interval between the ticks on the clock, which is in the Enterprise, is longer as observed from Earth than it is from somebody than it is as observed by somebody in the Starship Enterprise, for example, Captain Kirk. And once again, this time interval actually is longer. It's not any sort of illusion. It has nothing to do with how these events are observed, okay? The time intervals actually are different in the two different reference frames. Now I want to point out here that that this time dilation holds for two events that occur at the same location in one frame. So the clock is ticking off time, and those events, the ticks, actually happen at the same location in its rest frame. Okay, so now what about a clock that's ticking on Earth? Okay, what does an observer in the Enterprise, how do they observe that clock? Well, there's no preferred reference frame in special relativity. There's only relative motion, and so symmetry dictates that the time interval between ticks of a clock that's on Earth will be longer for Captain Kirk on the Enterprise compared to any other person, any other earthbound observer. Okay, and so this is an important principle when we're discussing relativity, is the lack of a preferred reference frame, and we'll get back to that again some other time.